Okay, so this is a companion video to using Hydra-Medusa to predict predominance diagrams. So if you haven't already, go back and watch the Hydra-Medusa video for predominance and fraction diagrams for anions. This one is going to be a shorter video that jumps straight into cations and gives you less practical knowledge about how to do that. So let's go ahead and do a model for chromium. So we'll go ahead and select chromium here, and I want, let's say, chromium 3 plus for this, and then we'll save this and open Medusa. Okay, so we're in Medusa now, and we have chromium 3. Let's start with a predominance diagram. So let's plot the log concentration of chromium 3. And I'm going to change my y-axis boundaries from log 0 to -6. So we're at 1 to micromolar. And then we're going to plot from pH -2 up to 16. And the reason I'm doing this is if you look at the figure on page 66 in your textbook, they show a variety of predominance diagrams for chromium 3 plus. These are the same ones I talk about in an actual video when discussing predominance diagrams for metal oxides. And so you can predict this. So now we'll just go straight to make a diagram. It's going to prompt me to ask whether or not this negative pH is reasonable. Choose enter if yes, and it is. It's going to compute that, and I'm going to end up with a diagram that looks like this, where I have the concentration of chromium as a function of pH over the range that I chose. And of course, at most acidic pHs, we're going to have the free ion. Know that that's not truly free, that's a hydrated ion, but we don't have any hydroxides from hydrolysis yet, which would occur under more basic conditions. And so when we're looking at these lines here, we can see that over here, we kind of have three major regions and then a couple subregions. So the major region to the left under acidic pH over pretty much all the concentrations is that we have the free ion. And then in the center here, we have Cr2O3, which has an oxidation state or an overall charge of 0. Cr stands for crystalline. That means that this is a solid chunk of chromium oxide. So this is the oxide that we're talking about. And then way over here on the bottom right, under dilute conditions and under really alkaline pHs, we actually can add another hydroxyl group here to resolubilize this and make this a negative charge. So we have 4 hydroxides. So this is the overall picture. This should match nicely with the picture that you see in figure 2.13, particularly version C. And if you want to look at version A and how this compares, that would essentially be a single cross section right here at log 0 at 1 molar, and whatever lines or boundaries you cross, those are the species that you see present in the most simplified version of the predominance diagram. These other little subregions here are the other stepwise reactions that are occurring, because we know that chromium 3 plus going all the way to chromium hydroxide, the solid or the oxide here, that's 3 steps. And so those subsequent steps are highlighted here, where you can see this is actually the first step between chromium 3 plus and chromium OH2 plus. And so this boundary here would actually be the pKa of this system, whereas the pH of precipitation would be defined as this leftmost boundary of Cr2O3, because this left boundary is the difference between any soluble species and a solid. And so there's lots of different predominance diagrams that people represent depending on what level of detail you want. In this case, this is representing a high level of detail. In some cases, some people would just collect all of these charged species on the left and call this chromium 3 plus, because this is essentially soluble chromium, whereas this is insoluble chromium. When you want a higher level of detail and you want to actually understand which species are present and at what concentrations, then you include all of these values like we have here.